So we're going to go over examples 2 and 3 in just a second. You guys are trying to finish up whatever work you were able to do. Hopefully you remember, thinking back to yesterday, why we're doing what we're doing. Forever card number 22. My silly way of remembering it, rolling flat. F of A has to equal F of B. If you were to draw a line between them, it would be a flat line. It would be a horizontal line with a slope of 0. So if you can roll flat between the two endpoints, then rolls applies. F has to be continuous on the closed interval. F has to be differentiable on the open interval. The endpoints have to equal. If that is true, then. Now, you guys see the theorem says a number, right? Then there is a number x equals c. Technically, I need you to think of that as at least 1. Maybe I should change it one of these days. I had it there originally, and then for some reason it got changed, his books got changed. But there is a number, at least 1 c. And c is just a special x value. Whatever, solve for x, and x will be c. But there's at least one place, one x, in between a to b, not including a or b, such that the derivative equals 0. So when we're doing this, just in case you're trying to do what I did in 2 and 3 and you're getting kind of stuck, help me out. How do you answer? And we can talk about number 2. How do you answer the continuous question? You look at the function and say, does he have any problems? How could problems come into a function for domain? For continuity. Kind of thing. If the function has a hole. But what would the function look like if it did have a hole? No. What would the function look like? What would the equation look like in here?
If it was a fraction that the bottom has a potential to be 0.
Exactly. The denominator has a potential to be 0. So denominators can have problems, but okay, the last one has a denominator, but the second one doesn't have a denominator. How else can a domain problem come up? No, those are just limits to infinity. That'll be a fraction, so denominators still. That's one case, denominators. What's another way a function can be limited? Even powered roots, square root, fourth root, sixth root, because you can't have negatives. Where else or how else can a problem come up? Logarithms, ln, any other sort of log, because remember, whatever's inside a log has to be greater than 0, greater than his vertical asymptote. And there is one more trick. Tangent, secant, cosecant, cotangent. What's wrong with them at some points? They have vertical asymptotes because you can write them as fractions with denominators again. Okay. Long story short, what did you guys think about number 2? Is he continuous?
No. Oh, yes.
Why? Can you plug in 0 and everything between 0 and 6, including 0 and including 6, and have it work out? Yeah, you'll get numbers out, right? Plug in 0, get a number out. Plug in 1, 2, 3, 4, 5, 6. You'll get a number out. So therefore, yeah, he's fine. Now he is a piecewise function, right? But that's still okay, because we're not really stressing about too much. Just can you plug in, can you do that? Yeah, that's good. So therefore, continuous check. But what do we have to think about as soon as we get to number 2? There we go. Okay, number 2, what are we thinking about? Differentiable. And what does differentiable mean? Who are we looking at?
Derivative.
The derivative. Or maybe the function if we know how the function behaves. For instance, you guys have seen some square root functions before, right? What do they seem to almost always have? A sharp point. Uh-oh. Well, maybe this guy's not differentiable everywhere in between 0 and 6. Not including 0, not including 6. But how would we check? We'd take the derivative. You guys reviewed this rule, right? What's the derivative of 3? Minus. Okay, what's the derivative of absolute value of x minus 3?
X divided by
U over absolute value of times u prime. Okay. All right, well that's exciting. What does he tell us? You can't take the derivative where? 3. If x equals 3, aren't I going to have a problem? Does that make sense? So if the derivative isn't going to exist when x equals 3, we're not even doing limits and that sort of stuff, even though the slopes won't agree. It is a sharp point. But if this doesn't work at 3, well, first of all, is 3 within? Oh, yeah. So therefore we can say, is it differentiable? No. Why? Because f prime of x is, do I put it this way? Discontinuous at x equals 3. If the derivative has a discontinuity in between, well, it's not going to exist there, so therefore the whole function's not differentiable there, which means, okay, theorem's off. Too bad, doesn't apply.
Wouldn't it be negative if there's a negative?
Well, a negative's on the outside, but remember, to be discontinuous, the bottom has to equal 0, which is going to happen when x minus 3 equals 0, add the 3. The negative, if we were to try to bring it in, would distribute, but we're not going to bring them in the absolute value because that's going to kind of mess up a little bit.
How'd you get the 3? Did you just like guess?
Oh, no, I saw a denominator and I set them equal to 0. Remember, domain, the bottom can't be 0. So when will this be 0? At 3.
And how is it continuous?
Oh, because I can plug anything into him, he's fine. F is continuous. F is not differentiable because his derivative doesn't work at 3. Does that make sense? So for number 1, look at F. For number 2, look at F prime. His differentiable derivative. So do I even have to worry about showing how Rolls applies? No, because he doesn't. Rolls does not apply. So I do not have to show anything guaranteed by the theorem that doesn't apply to this function. I'm done. Done, done, done. Number 3. But first of all, any quick questions on number 2? Okay. Number 3. I'm going to zoom in just because it's starting to get a little bit low down there, especially for people in the back. First thing we're supposed to check. What is it? Continuity. Okay, hold on. Wait a minute. What do I see right away? My eyes should just like, oh no!
-2.
I see a denominator. Okay, so x plus 2 can't be 0, so x can't be who? Okay, but why am I still going to say continuous with a check?
Oh, it's in warning.
Because it only needs to be continuous where? Is -2 a problem? No, he's outside of there. I'm not even looking at that part, so who cares? He's continuous on -1 to 6 because -2 would be out here, and -2 is my only problem. So if -2 is not included, then it doesn't matter. I'm good. Because remember, whenever we have an interval, we're talking about a range of numbers. So all we're looking at is here to here. He might have a problem over here, but that doesn't matter. We're just looking here. So is he good for all these numbers? Yeah. Because the only place he won't work is way over here. Now, we need to ask ourselves about differentiable. Uh-oh. Who do we look at for differentiable? The derivative. How do I find a derivative of a quotient? Quotient, well, you don't like it, but you can do it. Okay, tell me what to do. You should have hopefully already gotten here. Bottom to top? What's the derivative of the top? Minus, what comes next? Minus top. Times? Derivative of top. Good, just one. All over. Pause. What are you supposed to be answering with number 2 looking at the derivative? Yeah. When will, well, yeah. Is f differentiable? So you look at the derivative and say, when does the derivative exist? Always he's differentiable. F is differentiable. Ooh, not always. Ooh, f is not differentiable somewhere. Question, when is the derivative discontinuous? -2. But what did we already say about -2? Doesn't matter. He's outside of the interval. So therefore I can say, oh, f prime doesn't work at -2, but once again, -2 is not a problem. So we can say f is differentiable. Technically, according to the theorem, we're only looking at numbers in between -1 and 6. All of those can be plugged in just fine. Number 3, what do we have to check for rules? Do the y values match? F of A equals F of B. And F of A, we're talking about F of whose A? And who's B? So where are we plugging him into? Into who? Into the original function. So, I know we found the derivative. We're going to use him soon. Don't worry, it wasn't wasted time. We're going to plug -1 into the original. We'll end up with -1 squared positive 1 minus 2 times -1 plus 2, which is positive 3. -1 plus 2 is 1. Okay, there's 1. Plugging in 6. 6 squared is 36 minus 2 times 6 is 12. 36 minus 12 is? And 24 over 6 plus 2 is 8. Okay. What's going on? They match. So since condition 1 is met, condition 2 is met, condition 3 is met, what are we going to say about rules in this function? It applies. And since Rolle's theorem applies, it's our job to go looking for C. Well, how can we look for C? What does Rolle's theorem say? You have your notes right there. Just look up. There was a thing that we boxed. F prime of C equals 0. So if 1 and 2 and 3 are true, F prime of C must be 0 somewhere. What are they telling us to find? Where? So take F prime of C. Oh. Is it going to work better for your brains if we take the C and plug them into all the X's, or just stay with X's and at the end say, hey, he's C? Hey, he's C? Okay, so let's leave them X's. It might be a little easier. So let's go ahead and say, all right, if I want to set them equal to 0, do I have to simplify a little bit? So I'm going to start foiling the top. We have 2x squared. Check my math. This morning the math wasn't working out so hot. I did 5 minus 1 is 5. They got a little frustrated at me. It's okay. That's like me and grading your guys' stuff. Minus 2x plus. It actually makes me sad. It's so sad when you guys make a little mistake. Because I know it's just going to frustrate you. But it's okay. We find our weaknesses so we can make them
Oh, weaknesses.
backward. Okay, 2x squared. Do I have a minus 4x and a plus 8x? Is that x plus 2? Oh, yeah. Sorry, so minus 2 and then plus 4, which is going to be plus 2x? Minus 4? Sound good?
Yeah.
Don't kill a seal. Minus x squared plus 2x, right? Good so far? So then we have 2x squared minus 1x squared is just going to end up being 1x squared. We have a 2x and a 2x, which is a 4x, and then we have a minus 4. And then we have an x plus 2 quantity squared, and we want to set the derivative equal to 0. Because that is what rules guarantees that it must be 0 somewhere. What did I do at the bottom part? Multiply him to the other side. Or if you want to think about pitchfork, he's not going to make a 0. Or multiply him to the other side and it's still 0, right? So now I have to factor. Oh! Do you guys agree with period 1? It's x minus 2 quantity squared?
No.
Good. Hopefully not. Hopefully not. But what do I do?
Move that 4 to the other side. Not that
4
way.
and 1 doesn't work. 2 and 2 doesn't work. I need it negative.
Because you're at 4 of these.
X equals negative b plus or minus squared. You guys keep going. Oh, come on, I sang it last year.
4 times 1.
B squared minus 4ac. 2.
I forgot that was a thing.
So sad. Because how do you factor? You don't. You can't be factored. But there has to be a 0 because the theorem tells me, so I have to go looking for him. He's just a weird one. Now, if you really want to and you don't like the quadratic formula, you can complete the square. Have fun. Okay, so. Totally fine. So now what? Because some of you guys, you learned it completing the square, and you're like, I don't even know what that thing is. But most of us, you learned it, you just don't like it. But if you sing it, it makes it happier. So. I have 16 plus 16 is 32. 32, here's where I started making all my math mistakes this morning. 32 square rooted. Doesn't 16 go into 32? 2 times. And the square root of 16 is 4. We can make it a 4 root 2, right? Can I pull a 2 out of everything? The reason I'm actually showing my work is this morning I didn't, and I got mocked because I made mistakes. Whew! There we go. No mistakes when I show my work. Okay. Just saying. -2 plus or minus 2 root 2.
No. Box it.
Is that my answer? Right? Remember, I was looking for x equals c. X equals c such that the derivative equals 0. Oh, stink. What's root 2? What's 2 root 2? Any ideas? Maybe it might make it a little bit easier if you pull out a 2. That'd be a 1. Still technically plus or minus. Root 2. What's root 2? 1-ish. Yeah, good. Right? Less than 2, more than 1 is between root 1 and root 4. So he's 1-ish. If you want, you can say 1.5-ish. If I do 1 plus 1.5-ish times -2, is that going to be within my interval -1 to 6?
Yeah. Wait, no.
1
no.
less 1.5-ish times -2? That's like 2-ish times -2. That's -4-ish. That's way outside. What if I do 1 minus 1.5-ish?
Yeah.
Ooh, that'd be a 1/2-ish. And a 1/2-ish times -2 would be -1-ish. We're going to say he fits. If you guys get me a decimal, we'll see a little bit better why he fits, but he does. So we're just going to be able to take only one of them. We're only going to be able to take -2 less 2 root 2. Or the other form of writing that would have been -2 times 1 minus root 2. Same thing. So if I distribute, that'd be a negative, that'd be a positive, just like it's right there. Dun, 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 dun. Why didn't I do the other one? Because he was way more negative than this showed. He was like -4-ish, which would have been outside. Is that kind of okay?
Yeah.
Yeah, it's a wild quadratic formula, right? All right. Number 2. If you guys remember, this section had 2 names, or 2 theorems. One of them was roll flat. The next one is mean value. Yep. He's coming. Mean value theorem. Long story short, we can tilt the picture of rolls. We can tilt the picture of rolls. That might not make sense until we see some graphs, so hang in there. I'm going to go ahead and zoom out just a little bit. Actually, I'm going to zoom out a lot more. Go find a rounded box. Make him yellow. And say, ooh, he's important. Forever number 23. Look at us, guys. We're almost halfway there.
Isn't this only the 3rd chapter?
Huh?
Isn't this only the 3rd chapter?
Yeah, but remember, your book doesn't just have Calc 1 and CalcAB in it. Technically, it has CalcBC content too, because calculus in college, like undergrad, is usually 3 courses. Just keep going past CalcBC. It's pretty much just CalcAB and BC, so like Calc 1 and 2. So, roughly, we're going to have to do a couple sections from chapter 7. But we're not going to do chapter 8 or 9 or 10. Oh, just 8 and 9. So we're skipping most of 7, and then we're skipping all of 8 and all of 9. That's about right. This is a Calc 1, 2, and 3 book.
That's a lot thicker.
A little bit. Can you see my college textbook? He's here somewhere.
You're thick enough to kill someone, yeah?
It's a little thick. Here it is. Yeah, boxes. Here's my Calc 1, 2, and 3.
Well, that's a lot thinner.
There's a lot going on. But do you recognize that name? He's our guy. Just we have a nicer, newer, and more AP-ish book. Okay. Why is it called the mean value theorem? Why am I saying this? Because if you have some sort of meaning to the words that name the theorem, maybe it'll help you remember the theorem. Like IVT. What are the words that go with the letters? Intermediate value theorem. Intermediate, in between, in between. Oh, you go from here to here, you have to hit everybody in between if your function is continuous. The height example, I was 2 feet, now I'm 6 something, and I had to be 5 something, 4 something, 3 something, somewhere in life. Right? Right? And intermediate value theorem, the in-between values theorem. Right? EVT, ooh, that one's more recent. That was just last section. EVT, what's the names or the letters or the words that go along with that?
Something value theorem.
And true. For what? Intermediate in-between value theorem. F of C has to equal different K's. EVT, extreme. That's what 3.1 was about. Extremes, right? So extreme value theorem. Extremes. A continuous function or a closed interval has to have an absolute max and an absolute min. Has to have it. Not all functions do, but a continuous function or a closed interval does. And those absolute extrema will occur at either endpoints or critical numbers. That's EVT. What's this one going to be? MVT. Right? IVT, EVT, MVT. And MVT goes along with, and even the AP guys know MVT. If you ever write mean value theorem, you're just wasting your time. MVT. What does mean mean? Just mean? It's an angry little theorem. Average. Wait, why average? I don't get it. What's this? Oh, hey look! I wrote average right there. Who's average? Average rate. Who's average rate? Motion forever card. S of B minus S of A all over B minus A. Oh, that's this guy. Except instead of plugging in position, you're just plugging in whoever F is. There are many different ways of saying mean value theorem, but long story short, it's the generalized version of Rolle's theorem. Rolle's was found first. I kind of said this yesterday. He figured out if the two y values are equal, rolling flat, then I have to have, thank you, a horizontal tangent somewhere in between. A horizontal tangent somewhere in between. F prime of C has to equal 0 somewhere. But then this guy later was like, hey, I wonder if we can generalize it and just say the derivative has to be whatever the slope is in between the 2 points. And we'll see graphs to figure out exactly what all's going on. But long story short, F still has to be continuous on the closed interval, A to B. Same as Rolle's. F still has to be differentiable on the open interval. Same as Rolle's, A to B. But what's missing?
F of C equals 0.
What's the third condition that's missing?
F of A.
F of A equaling F of B. It doesn't say it has to roll flat. It just says whatevs. We don't care. It can be tilted. You don't have to roll flat. They don't have to be the exact same y value at the endpoints. It can be different. This way or that way or the other way. Just not that way because that's not a function. But it can be something else. And whatever that slope is, F of B minus F of A over B minus A, the slope between the 2 points has to be what the derivative is at least once in between A to B. Another way of saying it, the derivative, the instantaneous rate, another way of saying derivative, has to equal the average rate. Another way of saying it, the slope of the tangent line has to equal the slope of the secant line. But let's get some pictures so we can kind of visualize what's going on, okay? This is forever number 23. The wording, let's try to visualize, okay? But before we visualize, can we at least test it? Hey, this looks familiar. It looks a lot like the Rolly one. Do we still have to check 3 things?
Yeah.
Okay. You guys are okay? I thought I heard people needing last page. Sorry. We don't need to check 3 things. We only need to check how many? 2 things. So, number 1 is the function. Wait, you just wrote it. Number 1, is the function continuous? Is the function continuous on, technically, -1 to 2? Yeah, he's a what? He's a polynomial. Those are fine, right? They just go on forever? Okay. Or you can think of it, because you plug in all the numbers -1 to 2. Yeah, he's fine. Continuous, check. Differentiable. Oh, I don't know. I have to look at his derivative. Well, most of you know polynomials have smooth curves. That was from pre-cal. You can also just find his derivative really fast. Oh yeah, that's right. He's another polynomial. 1 degree less. Why is he 1 degree less? The derivative of a polynomial. Why is the derivative of a polynomial always going to be another polynomial but 1 degree less?
Because exponential decrease by 1.
The exponent decreases by 1 because of power rule, right? Anyway, he's still continuous because he's fine. No denominators, no square roots, no ln's or trig came in. So therefore, differentiable, check. Oh, we're done testing. Guess what? MBT applies. That's why usually on the AP, even though sometimes you can use rolls as a justification, for the most part they're like, hey, just use MBT because he works for everybody, whether you're rolling flat or whether you're tilted. But it's still good to think about rolls because he's this special case of, oh, the derivative can be 0. What do I do now? MBT applies. Good. Oh, you know what? We didn't box the conclusion on the page before. Hold on, pause. We did it for rolls. We forgot for MBT. If we know the 2 conditions, that's great, but we don't know how to finish off the idea. If number 1, if number 2, then box. F prime of C must equal somewhere. F of B minus F of A all over B minus A. So, wait, who's the F of A, F of B people? Well, A, they're not people, but B, who are they? What are they? How do we find them? Plug it in, plug it in. Plug in what? Plug in B, plug in A, right? To who? The original. Now I'm showing the work over here because we're going to put it all together in just a second. But if I plug in 2 to the original, 8 plus 2 is 10. 10 minus 6 is? Nope. 10 minus 4 is? 6. Thanks. Keep me honest. -1 cubed, -1 minus 1 minus 4, -6. Why am I doing that? Because I need them. For who? My formula. Give everybody a group high five or a pat on the head or a little shove on the shoulder to say, wake up. Heads up. No heads on books. No heads on bottles. No heads on anything that can make you rest. Make you rest and make you sleep. Alright, so how do we keep going? Your high fives are supposed to be quiet-ish. Okay, come back. F prime of. Do you guys like the C? Should we put them in or leave them out?
Leave them out.
Leave them out. Alright, so we're just taking F prime of X and saying whatever, whoever we find is the special C. Ethan, come on, bud. Head up. Equals 3x squared plus 1. What do I set the derivative equal to? What is the box for MVT? What's in the box for MVT? F prime of C equals who? Oh, F of B is 6 on this one. Minus who? F of A is -6 on this one, all over. B is 2 on this one, minus A is -1. F of B, F of 2, minus F of A, F of -1, all over B, minus A. We're plugging into the formula. Then all we need to do is solve for our special x, and our special x, hey, that's C. So, 3x squared plus 1 equals 12 over 3 is 4. True?
Yeah.
And then we subtract the 1, that's 3. Then we get 3x squared is equal to 3. Then we get x squared is equal to 1. Then we get x is equal to plus or minus 1. And that's all C, right?
No.
It's not a C. Why isn't -1 a C? The only guaranteed ones are within. So, the only guaranteed. That's right, we're supposed to say, hey, he's C. There we go. Dun, 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 dun. -1 was a place where the instantaneous equals the average, but not in between -1 and 2, so forget him. Just 1. Number 2, you guys. Take it away. Stay awake. Test 1, test 2, take a derivative, set them equal to F of B minus F of A all over B minus A. It's okay, he's doing it. He's doing it. Sleepily, but he's doing it. I'm gonna go stand over and inspire people.
Why
Come on, guys, I'm inspiring you.
Yeah, just fine.
Wow, Kyle, great. He's practicing.
It's because his mic can't. No, but he has a
Since
movement.
Sarah's in there, we say
And it can go as fast as
So, my inspired people, what'd you figure out?
Zero can't work and that's a
Zero can't work in F, so?
So MPT does not.
This is your favorite one ever?
Yes.
Oops, I lost it out. Done. So not to go any further. Because I have nothing guaranteed, because MBT doesn't apply. Can we keep going? Here, too much excitement. Wait a minute! Why is there a graph with a line going through A and B?
Because that's the MVP.
What's a line that cuts through instead of skimming? What's he called? Tangent, skim.
Secant.
Secant lines cut through. Wait, no, secant lines only touch in 2 places, and this one touches like at 5. In circles, secant lines can only hit in 2 places, but in other things, as long as they cut through, I guess they could hit however many times they can hit. So long story short, who's this? A secant line. How would you find that slope of that secant line?
Opposite of Kennedy.
Wait, that's a tangent line. Hold on. How? You have 2 points. It's going through A and it's going through B and other random stuff, who knows who they are. But whatever, it's going through A and it's going through B. So what do you do? Y2, right? Y2 minus Y1 over X2. Who's that? Oh, B. Minus X1. Oh, that's A. Wait a minute. How do you find Y's if you know the X's? Oh. So this whole F of B minus F of A all over B minus A is really just a Y2 minus Y1 over X2 minus X1. He's the slope of the secant line. That's all he is. He's just a slope crashing through the graph. Now the question up here says, all right, assume, and it kind of looks like it, that this function f is continuous and differentiable on a to b. Maybe he has problems somewhere else, but right here he's good. Continuous, differentiable, continuous on the closed, and differentiable on the open. We want to eyeball where the C's are. How are we going to do that? Can you guys figure out how many places, wait a minute, wait. This is the slope of the secant line. This is the slope of the line that cuts through that I can see right here that's kind of positive-ish. Maybe not super high, but kind of positive. Who's this the slope of? Now, Jacob. Well, here's the derivative, and the derivative is the slope of which line? Yeah. And how do we see tangent lines on graphs? What do? Not cut through, they skim, right? And in order for the slopes to be the same, wait a minute, what are the lines, how are they related if their slopes are the same? They might be in different places, but they are parallel. Oh, hold on. Take your little hand, or your little imaginary line, and start skimming it. Say, when's it going to be parallel?
Yeah.
1-ish, 2-ish, 3-ish, 4-ish, and that's it. And if you're not quite sure what I'm trying to show, we can just take this line and say, hey, where would he skim? Oh, looks to be about there, right? That'd be one skimming one. That'd be a place where the tangent line. So wherever he hits would be one C value. Remember, there can be more than one. At least one C. Where else is there going to be one? Where's he skim? Right about there, yeah? There's another C, a little bit past the minimum. Alright, there'd be like C2. You could approximate and count them, but time's too short. Now what? There's a C3-ish. There's a C4-ish, right? C4-ish. And then where's he hitting? C3-ish. So question, kiddos, if you had his formula and you solved and found f of b minus f of a all over b minus a and set the derivative equal to, how many c's would you have found?
4.
Exactly. So we can kind of eyeball it and see on a graph what this idea is. It's saying, hey, there are going to be some lines that are skimming the graph, some of these tangent lines that are going to be the exact same as the one that cuts through. Hence, rolls tilted. Doesn't have to roll flat in between. But whatever slope it is indicated by this little formula, and the derivative will have to be that, as long as the function is continuous on the closed AB, differentiable on the open AB at least one time. This one just happened to be 4. Now, it just got a little more specific. Same idea. They got a little more specific. Question. They tell us use this function on the interval 0 to 7 and figure out about where the mean value theorem works. Huh? Find the C's again. But we can't start finding the C's until we figure out who they're supposed to be parallel to, so what are we going to do? Find the secant line. I could get that, but I'm trying to draw it. Secant line seems to have the point 0, 1-ish. And then, 7 is the end, right? 7, okay. That looks like a 6, but it's really a 5. I made that mistake too. This morning it was rough. That's a 4, that's a 5. Looks like a 6. Anyway. I could make it 5 point something, but let's just go ahead and, for sake of simplicity, just make it 7.5. We'll round down. Sound good? It's definitely less than half. This is the line we're trying to make things parallel to. Technically, what is the slope of that line? How would we find it? F of b minus f of a all over, see where I made my mistake this morning too? B minus a. We're looking who has a slope of 4/7. Now guys, we don't have an equation, so we can't be super precise and set the derivative equal to that. If we did have the equation, that's what we would do. But since we don't, what are we going to do instead? Skim and say, you look parallel. Maybe it doesn't look parallel we want. I look parallel. How about this one? Is that a little better? Okay. There's one. Anybody else?
Yes.
There's another one. Okay. Judge not lest you be judged. Okay.
That means parallel.
Looks roughly, right? So then we could approximate and say C is approximately 1-ish and approximately 5-ish. Just saying, we have to eyeball on graphs. We can't. We're looking for when are the skimming ones, the tangent lines, parallel to the secant lines. Now, what if you had something like this? Wait, we've been talking about secant lines. Are they really that scary? How do we find the slope of a tangent line? We plug into a derivative. How do we find the slope of a secant line? We plug into our nice little slope formula. How do we make an equation of a tangent line? We plug our point of tangency, into our point slope formula. How do we make an equation of a secant line? Oh, we have 2 points. We just picked one. It could be f of b with b, or we could also do who? F of a with a. It doesn't rightly matter because if 2 points are on a line, they're going to have the same equation when you simplify. Kiddos, this is good stuff. We've gotten to the end for you guys to be able to fully attempt section 3-2 for tomorrow. Tomorrow, after we create our evens of our homework, meaning you haven't have to do section 3. You might get stuck that we're going to work on a few word-ish problems. We're going to do a few deeper problems tomorrow, so do as many of the ones you can do. Basically, do everything but maybe the wordish ones. Do your best, and then come tomorrow to get a little more help. Sound good? All right, we're out of here. Bye, guys. Carla.